Thank you, Danny, and thank you for the invitation to come here again today to talk about something that I don't know if it's going to be what you expect to be, but it's a little bit out of frustration of why we can't understand carbohydrates and why we can't understand fiber feeding of pigs. So I'll try and, if nothing else, share my frustrations with you here today, and maybe some of you can help me get going. A few take-home messages that I hope you will leave with from today is, first, fiber is incredibly complicated. Okay, and I'll talk more about that later. I've worked a lot with amino acids, I've worked with lipids, we work with minerals and so forth. Nothing is as complicated as fiber. So that's the first appreciation you have to have, and maybe one of the reasons for my frustration on this. The second thing is that there are some real barriers in fiber that hinders fermentability of those fibers. And I think until we understand those barriers, and I'll try and talk about some of them, but until we understand them, our chance of succeeding in increasing fermentability of fibers is probably not very good. So we really need to focus on that also. Talk about enzymes a little bit, and I've come to the conclusion that unlike when we talk phytase to increase phosphorus digestibility, if we want to do something to increase fiber fermentability, we have to have more than one enzyme. And I'll show you why I believe that's the case. We need to have mixtures of enzymes. And I'll try to make that point to you. And finally, maybe to really get a breakthrough in this area, we need completely new technologies. Maybe we need the paradigm shift that Dr. Easter was talking about before. And maybe I'm too negative on this, but I think we may have to do something really different from what we have done in the last 15, 20 years in terms of fiber fermentability if we are to really make pigs utilize fiber better, okay? So those are the take-home messages that I hope you'll leave with here from today, and I'll try to make my case for each of these points. Now, before I start, I want to acknowledge my two good-looking co-authors here, Mr. Diego Navarro and Diorabella Abalilia. And Diego and Diorabella, they have done a lot of the work that I'll talk about today. They have prepared some of the slides that I'm going to show you and put a lot of effort into it. So I do want to acknowledge that. They are both PhD students in my lab, and they are both supposed to finish next spring. So we'll see how that works. Now, we talk about fiber. Starting with this slide here, nothing you haven't seen before. If you look at the total energy in corn and DDGS, we have quite a bit more energy in DDGS than we have in corn, right? But if we put it through the pigs and look at what the pig can metabolize, there's no difference. That means the huge advantage that DDGS had here had somehow disappeared when we fed it to the pigs, right? So if you look at that in a different way, you can say that the undigested energy we have in corn and in DDGS, it's very different. We have 440 kilocalories per kilogram of corn that doesn't get utilized by the pig, but we have more than 1,300 kilocalories in DDGS. And the majority of that undigested energy is fiber. So that, to me, that shows the potential we have if we could make DDGS as efficient as corn in terms of utilization. We have almost 1,000 kilocalories here we could add to the pigs. That would increase our efficiency quite significantly. So that's really the potential we have, and that's why it's important to talk about fiber, in my opinion. Okay, so let's talk about carbohydrates. Let's see what carbohydrates really are. And I said it's complicated before. All carbohydrates come from monosaccharides. I'll talk more about monosaccharides here in a second. Then from there we get disaccharides, oligosaccharides, and polysaccharides. That's not too complicated. We have the disaccharides here, we have different oligosaccharides here, and then the polysaccharides we have starch and glycogen, and we have non-starch polysaccharides. Some of these carbohydrates are easily digested, starch and sucrose and so forth, but some of them, all the yellow ones here, are not digested, they need fermentation. Okay, and that is what we call fiber with a big term. It's all these, a couple of disaccharides, it's all the oligosaccharides, and the non-starch polysaccharides. Okay, so it's a pretty diverse group, and we'll try and talk a little bit about those. But first, the first thing we need to understand is the building blocks, the monosaccharides. And if you talk about proteins, there's no doubt, we know there's 20 amino acids that are needed for protein synthesis in a pig. We never discussed that. There's no doubts on that. That is very clear. Fatty acids, we understand fatty acids. Minerals, macrominerals, microminerals, vitamins, we understand all that. But monosaccharides, we don't even understand the monosaccharides that we have in our fibers. Right? And you'll still see new published papers say, hey, we found a new monosaccharide in this fiber. So that is a little bit frustrating that we don't even understand what we have in these fibers. So talk a little bit about these monosaccharides. Some of them are pentoses, meaning they have 5 carbon sugars. 3 of them here we'll find in the feed, at least arabinose, xylose, and apiose. All 3 of them we'll find in different parts of our fibers, right? You can see the structure here if you want to memorize that. We also have hexoses, and that's a bigger part of our fibers. 4 hexoses here: glucose, fructose, galactose, and mannose. We have those in our fibers also. That's not complicated. Now we have 7 already. But you'll see we can modify these hexoses. So we get something we call deoxyhexoses. And now this was glucose before, but now instead of having a CH2OH group here, we have a methyl group. So we took the oxygen out, and now we call it rhamnose. And that complicates things quite a bit. And rhamnose we find in some of the fibers that are most difficult to ferment. We have fucose also, that's synthesized from mannose. And the structure of these deoxyhexoses is similar to glucose, except that they have 1 less oxygen. So it's C6H12O5. We have a couple of other deoxy sugars, also DHA and KDO, and they are 7 and 8 carbon sugars that we will find in the fibers. Not very well defined at all, but we will find them in some of our fibers. So we have these deoxyhexoses. And then we have another big group that's called uronic acids. And these are, you'll see here again, glucose, but now we have an acidic group here. So we don't call it glucose anymore, now we call it glucuronic acid. And we have glucuronic acids, we have galacturonic acids, and aceric acids from methanol. So we have 3 of these here. So if you've followed me so far, we have at least 14 different monosaccharides in our fibers. And there may be more. And then we have, as you'll see here later, we have associated compounds, acetyls and methyl groups, and we have phenolic acids that are associated with the fibers. So that's part of why this is complicated. And we don't really understand all of these monosaccharides. So if you go back to our overview here, and I told you before, the fibers are all the yellow ones. All the disaccharides and the oligosaccharides here, pretty much all of them are relatively easily fermentable. So that's not where we have the problem. So they are fermentable in the large intestine, some in the small intestine by the pigs, and absorbed. So really the unfermented part is down here in the non-starch polysaccharides. Okay? So let's try and look at the non-starch polysaccharides. They consist of cellulose. Some of them are cellulose, as you all know. I'll talk a little bit more about cellulose in a little bit. And some are non-cellulosic, non-starch polysaccharides. You may also call them hemicelluloses, same thing. If you look at those non-cellulosic, non-starch polysaccharides, we can divide them into pectins, or pectic non-starch polysaccharides, and non-pectic, non-cellulosic, non-starch polysaccharides. So I kind of hate to define something by what it's not, but that's exactly what we are doing here. They are not pectins, they are not cellulose, and they are not starch. So that's what we have left here. In those components, we have arabinoxylans, we have mixed-link beta-glucans, we have xyloglucans, and we have mannans. So those are the 4 groups that we have here we will find, and I'll talk about some of these in a little bit. Then we have the pectic non-starch polysaccharides. That may be, these pectins are the most complicated group to understand. Those are the most complex structures we will have. And among those, we have something we call homogalacturonin. We have rhamnogalacturonins. We have rhamnogalacturonin 1 and 2. We have arabinins and arabinogalactans. arabinogalactan 1 and 2 also, so there are 2 of those, and we have some silogalacturonins. Now, one thing that's a little bit makes it a little bit easy are the names that all our non-starch polysaccharides have. The last part of the name usually refer to the backbone of the fiber structure. And the first part usually refer to the major monosaccharides that is not in the backbone. That's usually the way it is. So if something is called a galactan, that means there's a galactose or galacturonic acid in the backbone. If it's a xylan, there's xylose in the backbone and so forth. So that's how they are all named. Okay? So if we look at cereal grains, and we feed a lot of cereal grains to pigs, grain co-products, what are the fibers we have there? We don't have all of the fibers that I just listed. We have some of them. Cellulose we have arabinoxylans, we have mixed-linked beta-glucans, we have xyloglucans, and we have galactomannan. But you'll see we don't have the pectins here. We don't have the pectic polysaccharides in our cereal grains. So that's the difference from the oilseeds we'll come to later. So we have these components, and then we have another component here that is associated with the fibers, that's lignin. And lignin is maybe the biggest barrier we have for fermentation. So every time we have a fiber that's lignified, it's pretty much a certain thing we can't ferment it. So as long as we have lignin attached to our fibers, they are unfermentable. So that's one of the barriers we have to fermentability. Lignin is not a fiber, but it's primarily phenolic acids, but it's associated with the fiber fraction. Okay. How much do we have of this? Well, if you look at the different cereal grains, corn, 8% approximately total dietary fiber, wheat a little bit more, barley more again, oat is the most fibrous one of all our cereal grains with more than 30% fiber if you include the hull. And then we have rye, a little bit less, sorghum, 20 to 25%, and then we have rice here with the lowest amount. This is polished rice, so this would be if you feed broken rice, that's what you would get there, right? It's not, we're taking the hulls and the brands off this rice. So quite a bit of differences, but this is in the cereal grains, and then when we come to the co-products, we have much more, as you all know, corn germ meal or corn DDGS, we have much more fiber in those because we have taken the starch out. What is the composition of this fiber? If you look at corn, cellulose is 25 to 30% in corn, and in the orange here I put up DDGS also. You see about the same amount, 25 to 30% cellulose. And then we have arabinoxylans, and that's by far the biggest part of the fibers. And that's true for most of the cereal grains. Arabinoxylan is 50 to 60% of all the fiber. Okay, and then we have the others here that would be much smaller components. And that includes lignin also here. So a couple of points here. One is, if we want to do something about fiber, it would make sense to really focus on the arabinoxylans because that's the biggest group, and that's true, as I said, for most of our cereal grains. Another point, if you look at DDGS and corn here, they are pretty similar. What does that tell you? Well, to me, it tells me that it's probably there's very little fermentation of fibers or hydrolysis of fibers in the ethanol plant. That they, despite all the enzymes they use in the plants, they don't really degrade much fiber in the ethanol plant because you can see here it's pretty much the same thing between the two, right? So I think that's another conclusion we can have. I'll come back to talk about both cellulose and arabinoxylan here in a minute. I just want to show some of the other fibers we have in cereal grains. These are mixed-linked beta-glucans and also arabinoxylans we have here. Lots of arabinoxylans in corn, as we just saw. Basically no mixed-linked beta-glucans. Wheat, we have some of the mixed-linked beta-glucans, a lot more arabinoxylan also, barley more, oats and so forth. So again, arabinoxylan is a big significant part of the fibers. Cellulose and lignin. Cellulose, as we saw before in corn, about 2% in whole corn, wheat a little bit less, barley and oats also. And then we have the lignin. You see how much lignin we have in oats here. So pretty big component here. Now, talk about cellulose. What is cellulose? Well, cellulose is glucose. So it's pretty much starch, except we have a beta-1,4 bond instead of an alpha-1,4 bond among these glucose units. So cellulose looks like this. It's long chains of glucose linked together by these beta-1,4 bonds that pigs cannot digest, or animals in general cannot digest. So then there can be up to 15,000 glucose units in each of these long chains. And because it's linear chains, they can pack very tightly. So that's what you see here. They are packed very tightly, and then there's hydrogen bonds between these different chains, which makes them very unfermentable. The enzymes simply cannot get access to those bonds. So that's why this is very unfermentable. However, you'll see we did have a little bit here where it's not quite as packed, and we call that amorphous cellulose. The other up here that's very tightly packed, we call it crystalline cellulose. The crystalline cellulose is very unfermentable, but there is a chance we can ferment some of the amorphous cellulose here because the enzymes can get access to it. What are the enzymes we need? Well, we need an enzyme called glucanase that can hydrolyze here in the middle, and we need exoglucanase that will take off 2 units at a time. And then we need another enzyme, beta-glucosidase, or you can call it cellobioase, to hydrolyze the last ones here. So it is possible. It's only 3 enzymes we need. However, the bad news is for animal feeding that these enzymes, they are relatively slow. And I've been told by enzyme companies that they can only hydrolyze 1 bond per second. And to me, that sounds pretty fast, but they say that's way too slow to make a difference. So we cannot use cellulase enzymes, these 3 enzymes, really to make a difference in the pigs in general. And again, I go back to the ethanol plants and say, if anyone could figure it out, it would be the ethanol people, because they can control time, temperature, and pH, which we cannot control in a pig. And the ethanol people cannot figure this out. And that would be huge value to them, because they could make all this glucose into ethanol, right? So if the ethanol people can't get it done, in reality, it's probably unlikely that we can get cellulase enzymes to work in pigs. It's just my conclusion. Maybe I'm wrong. Maybe somebody can figure it out one day. But again, I think the ethanol people will figure it out before we do, right? So probably not that likely we will do it. So that was cellulose. Mixed link beta-glucans, they are similar to cellulose in that they also consist only of glucose. But here, instead of having only beta-1,4 linkages, we have some beta-1,4 linkages here. We also have some beta-1,3 linkages. And that means that we get kinks in this chain. So it's not a long chain of glucose anymore. It's kinked like this. And 30% of all the bonds are beta-1,3. So it cannot pack tightly. And that makes all the difference in the world, because now the enzymes can get access to these bonds, and this mixed link beta-glucan, that's easily fermentable by the pig. So it's really the ability to pack those cellulose together, that's what makes them unfermentable. Mixed link beta-glucans are pretty much 100% fermented in the digestive tract. The bad news is we don't have any mixed link beta-glucans in corn, as I showed you before, so it doesn't help us much. But in barley and in oats and other cereals, we do have them. There's 2 enzymes needed here. As I said, there they are, endo-beta-1,4 glucanase and endo-beta-1,3 glucanases. And they are microbial enzymes, they can easily ferment them. Then we come to the arabinoxylan. And now it becomes more complicated. The first 2 I talk about, cellulose and mixed link beta-glucans, only glucose. We call them homopolysaccharides, only one polysaccharide. Now we go to heteropolysaccharides, and you'll see a number of different compounds listed here. That's what we find in our arabinoxylans. The backbone, as the name suggests, xylan, so the backbone is all xylose, okay? And then we have side chains here. Major side chains are arabinose, and they are linked, and we do have some galactose here, and we also have a glucuronic acid here, and they are attached. A couple of points. First, if we could completely hydrolyze this structure in the small intestine, we would get absorption of a lot of xylose and a lot of arabinose, right? However, that is not going to do us any good, because these, as I showed you before, these are pentoses, these are 5-carbon sugars, and they cannot be utilized in metabolism. So they would all end up in the urine. So the goal here is not really to hydrolyze arabinoxylans completely in the small intestine and absorb all these 5-carbon sugars, because they will be excreted. So the goal would be more to somehow enable the microbes to ferment this arabinoxylan in the hindgut. And how do we do that? Well, you all know there's a lot of xylanases on the market. It's an endoxylanase. It's supposed to cleave the backbone here, right? When we talk about corn, and I'm just telling you my experiences, it is incredibly difficult to make xylanases work consistently in corn co-products and in corn. In pigs. Maybe in poultry a little bit different, but in pigs it's incredibly difficult to consistently get a response. Okay, so if you add this endoxylanase, we don't have very good luck with that. Why is that? Well, maybe one of the reasons is that we need 8 other enzymes to completely hydrolyze this structure, right? We need a total of 9 enzymes to hydrolyze arabinoxylans. And you'll see them, there are different ones here to cleave the different bonds, but as long as we only provide one enzyme, we may not have a good chance of being successful. Now, we may not have to provide all of these enzymes, because the microbes, they can help us. But we probably need more than just one enzyme. And then we have another complication here, and these are the 2 structures here, ferulic acid and coumaric acid. Those are not monosaccharides. So those are other structures that are attached to the arabinoxylans here. And you'll see they are here. And the significance of these 2 structures is that they can attach to lignin. So every time you have ferulic acid and coumaric acid, you also have lignin. And lignin, as I said before, is a major barrier for fermentability. So every time you have these compounds here, you have lignin, and you have pretty much, you have an unfermentable substrate. So the first prerequisite for getting this fermented really is to get this one taken off. Get these coumaric acid and ferulic acid taken off, so we can delignify the fiber and then let the microbes work. So how do we do that? Well, look at the name here. We need an esterase, right? So it really would make sense to add esterases into the mixture. And there is research published with esterases, some of them successful, some of them not. But I think that's the first prerequisite for getting arabinoxylans fermented is we get rid of the lignin, and the only way, if we do it enzymatically, is with esterases, right? So that's my conclusion here. We need that. And you'll see that there are people who are selling xylanases who also add arabinofuranosidases into the mixture. They may declare it or they may not guarantee it, but it may be in the mixes, at least from some companies. I'm not sure all of them do it. Some companies have told me, we've discussed this, yeah, we only guarantee the xylanase activity, but actually we don't clean it up completely when we synthesize it, so there is some residual activity of some of these other enzymes there. We just don't know how much it is, and we don't know if it's there all the time, but there may be some of these other enzymes here. But I think for arabinoxylans, which is the most predominant fiber part in our cereal grains and grain co-products, we really need a mixture of enzymes, and the esterase should be the first one we look at. Just my opinion, based on what I know. Now, it's not all bad, because enzymes, sometimes they do work. I want to show you an example here. The xylanase we added to brown rice, full-fat rice bran, and defatted rice bran. We published this last year. And you see brown rice, we didn't see any effect of the xylanase in the orange bars here with xylanase, blue bar, no xylanase. And that makes sense because in brown rice, it's primarily have starch, so you wouldn't expect any effect here. But in full-fat rice bran and defatted rice bran, we have at least a 10% improvement in metabolizable energy here. So that looks pretty good. You may wonder, why am I showing rice bran here, and why is it not corn? Well, the obvious reason is I don't have any data on corn. I don't have any data on corn or corn co-products that shows this effect. We have it in rice bran, we have it in wheat and wheat co-products, but we cannot make it work in corn. If I had data on it, I would show it to you, but we just don't have it. And it's not because we haven't tried. I don't know how many experiments we've done with xylanase and corn co-products. We just cannot make it work. Okay? So xylanase, it can work, but we probably have to look at the ingredients. Okay? Another example I have here, we tried to, and we thought we were smart, this delignification was something we wanted to look at. And so we tried to do some physical treatments with extrusion. We tried to do chemical treatments either with sodium hydroxide or calcium oxide. And then we had a couple of enzyme treatments here. And in this case, there was cellulase and xylanase mixed together. And we had another one where they said it was a mixture of hemicellulases and xylanase mixed together. And the only thing here we could make work was actually the enzyme treatment here with cellulase and xylanase. You can see we had a significant increase in digestibility of energy in DDGS when we added that. Our chemical treatments didn't work in this case, extrusion didn't work in this case, and the hemicellulases didn't work in this case. So I guess what I'm saying is, it's not all bad. There are some good results we can have even in corn fibers, but it's far between. We get a positive response. And in this case, we were not successful with the chemical treatments either, which we had hoped we could delignify using this, because in ruminants it has been shown repeatedly that sodium hydroxide treatment or calcium oxide treatment will improve dry matter digestibility. So we had hoped we could see that here also. That was not the case. Okay. So how am I doing on time? Conclusions on cereal grains is we should focus on arabinoxylans. That's the most common one. We have to have. We don't need to have complete hydrolysis in the small intestine. That's not the objective, because we don't want the 5-carbon sugars being absorbed. They need to get into the large intestine. And finally, we should use multiple enzymes to get hydrolysis. Those are the conclusions I have on cereal grains. What about the oil seeds? Well, we have different fibers in oil seeds here. And if you look at the fibers here, we have oligosaccharides, and I have soybeans in blue, canola meal in orange here. We have oligosaccharides. Those would be stachyose, raffinose, primarily in soybean meal, not so much in canola meal. We have cellulose again, like in the cereal grains, and again we have less in canola than in soybean meal. But then we have pectins, or pectic polysaccharides. And that's the biggest part of the oilseed meals here. And then you'll see canola has a lot of lignin. And that's one of the reasons canola is so difficult to ferment. So what is these pectic polysaccharides? That's number one. We don't have the arabinoxylans here. We have the pectic polysaccharides. I showed you before we have homogalacturonins, rhamnogalacturonin, we have arabinins and arabinogalactans, and we have one more group here, the xylogalacturonins. Okay, I showed you that before. So quickly, I'll show some structures to you here to make you appreciate what this is. The first one is homogalacturonin. Galacturonin acid backbone, and then we need these enzymes here. There's 6 enzymes needed, and there's different methyl groups and acetyl groups here also attached to it. And actually, if you go out and buy pectin, you can see you can buy with different methylation characters, and that influences the gelling properties and so forth of that pectin. This structure is easily fermentable, pretty much 100% fermentable by pigs. So microbes, they have all of these enzymes we need here. You can see where they're coming in. Not a problem at all. We don't have much of this in our oilseeds, though. This is more in the citrus. Rhamnogalacturonin 1 is here. And this is a little bit different because we have the galacturonin acid in the backbone, but we also have rhamnose. So remember, rhamnose was the deoxyhexose from glucose. We have that in the backbone here. Every other one is rhamnose, every other one is galacturonic acid. And then we have some pretty complicated and big side chains, and we have side chains to the side chains here, right? This is complicated, and this can be lignified also. And this is very difficult for pigs to ferment, for monogastrics in general to ferment. And it gets even worse if we go to aramidogalacturonan 2. You can see all the structures you have here. And I won't go through them. In this case, the backbone is all galacturonan acids, but then we have these long side chains, and you can see they have different names, and there's a number of different monosaccharides and other structures that are included there, right? So you can see all the enzymes that are needed here to degrade these structures. And it is pretty unfermentable to pigs. I think goats in the rumen can probably ferment some of it, but pigs in the large intestine, they just can't do it. So that's why fiber from canola meal is very unfermentable in pigs. It's because we have these structures there. We have arabinogalactans here. I'll just go through a couple of them. Arabinogalactan 2 is this one with some arabinose on the side chains on a galactose backbone. And those are the fibers we have in the oil seeds. Very difficult to ferment, very difficult to ferment. And that's why we canola, sunflower, cottonseed fiber is very unfermentable. What are the conclusions on these oilseed fibers? Pectic non-starch polysaccharides are the major components we have in these fibers. I showed you that. And they are complicated structures, and then they require multiple enzymes, and therefore they are very difficult to ferment. And these fibers are really not the focus of the commercial enzyme industry. You don't see commercial enzymes being sold to help us ferment the fibers in our oil seeds. So that's a very different approach than to the cereal grains, right? A few more things here. We could talk about fiber. We can talk about soluble and insoluble fibers. The soluble fibers are very fermentable in general. 92%, you see here, total dietary fiber, 49%, but the insoluble dietary fiber only 40%. So solubilization seems to be the key. If we could solubilize fibers, we could get much more out of them. The bad news is that we don't have a lot of soluble fiber in our feed ingredients. And this is in DDGS, and you'll see by far the most is insoluble fiber here. But again, I come back to the physical treatment, chemical treatment, enzyme treatment. If you can use any of those things to solubilize the fibers, then probably the pig could do the rest of the work with the aid of the microbes in the hindgut. So I think those are things to think of in the future, maybe. And I go again back to this slide here where we tried these things, we were just not successful. And this was the reason we wanted to do this chemical and physical treatments. We were not successful in this case. Maybe we did it wrong. Maybe there are other options. I think there might be opportunities in this area if we did it. Okay. Other ways to improve fiber utilization. Just briefly, we worked a little bit on direct fed microbials, and usually we don't feed direct fed microbials to improve fiber. But if you look at what direct fed microbials or probiotics are supposed to do, they'll grow bacteria, increase lactic acid and acetic acid, and reduce pH, and they will increase fermentation, right? And some of these microbes that we get here, they actually secrete fiber hydrolyzing enzymes, so they potentially could help us, right, in increasing digestibility of fiber. So I'll just show a few numbers from an experiment where we fed lower high fiber diets from weaning to finish. And a couple of things I want to highlight here. We started out right after weaning with 10% wheat middlings and 10% DDGS. And then after 2 weeks, we moved DDGS up to 15%. And after day 43, when they came into a growing period, we got them 30% DDGS and 15% wheat mix. So relatively high fiber diets all the way through. Performance here, body weight started at the same weight, a little bit separation here after 2 weeks, and after on day 43, you will see the groups on the high fiber diets, the green bars, they were 1 kilogram lighter than the ones on the low fiber diets. Right? So we have, I should say that the orange are the low fiber diets, either without DFM or with DFM. So the scratched here are with DFM. High fiber diet, the green, and high fiber diet with DFM, this one here. So DFM didn't do anything here, but the high fiber diet reduced weight out of the nursery. However, Average daily feed intake was lower for the high fiber diets. You're not surprised by that because they are more bulky, and that probably means something here. And you'll see overall there's an effect of fiber on feed intake. Average daily gain, same thing, fiber reduced average daily gain in the second period here, and overall, not a big surprise either. If you add a lot of fiber there, you get a little bit reduction in gain. Gain to feed, no difference as an effect of fiber, but the DFM increased gain to feed. And we've actually seen that before in the grower studies, that DFM increased gain to feed, indicating we get a little bit better utilization of the feed if we add DFM to the diet. That was true in the first period here and for the overall period. And if we do the gain to feed as on an NE basis, we saw the same thing again, which basically just indicates that we have the right NE values for our fiber ingredients here. Short-chain fatty acids also increased with the high fiber diets, as you would expect. No surprise there. You get more fermentation, more short-chain fatty acids synthesized. And on day 43, we killed 1 pig per pen and did some different measurements. One of them was some gene expression in the liver, and there's a protein here called MCT1, which is a transporter for short-chain fatty acids, and you can see the DFM increased that in both types of diets here, so indicating more short-chain fatty acids coming to the liver, more expression of this enzyme here. And we also had a couple of other genes, CD147, that's a gene that's used to relocate the MCT1 gene to the surface so it can transport. That has increased transcription also, and we have GLP2 receptor protein here that also was increased, indicating an increased ability to metabolize primarily sugars and glucose in the liver. So some positive aspects of DFM in this case, at least, maybe not always on fiber, but in this case, we did it. We kept the pigs we didn't kill. We had 5 pigs per pen. We killed 1, so we had 4 pigs left. We took them to the growing and finishing facility, and just looking at the body weight here, remember at the end of the nursery, we had a 1 kilogram reduction in body weight gain here on the high fiber diets compared to the low fiber diets. But if you look here during growing finishing, they actually caught up. And at the end, there was absolutely no difference, right? So although we saw this reduction in gain in the nursery, overall for the entire wean to finish period, there was no difference. Indicating to us, and I've tried to make that argument before, maybe fiber should be fed from weaning, because I think you increase microbial populations, as we saw with the short-chain fatty acids, and then they will catch up in grow finish, even if you sacrifice performance a little bit in the nursery. So that may be something to think about. Feed intake increased overall as we had higher fiber in the diet, no effect of the DFMs in this case. Daily gain was not different overall. There were some differences here, higher in the first period, no difference in the middle, and then a little bit lower towards the end, but overall, absolutely no difference. And gain to feed, there was a reduction on a kilogram per kilogram basis, as you would expect, because we have less energy in the high fiber diets, but actually, I didn't bring those data. When we calculated on an NE basis, there was no difference here either. So again, indicating we have the right NE values. So fiber can be used successfully in some cases, and we've done this before in many experiments. Conclusions overall, I hope I've convinced you that many fibers have very complicated structures, right? And that's part of the frustration we have, why we cannot ferment these fibers very well. Fiber analysis is not very accurate. I didn't talk about that, but the fiber and our ability to analyze these different fiber components is not very good. We can analyze a lot of things, but the different fiber components are very difficult to analyze. So that's one complication also. And I think there's a big potential for improved energy utilization from fibers if we can solve this question. What else? Enzymes and possibly DFM may improve energy utilization. We just need to get better at it, and in some cases, In some cereal grains, it's easier than others. Wheat and rice, much easier to make enzymes work than in corn. Unfortunately, we feed all the corn here, so that doesn't help us much, but maybe we can make it work at some point. Other procedures to delignify and hydrolyze fiber are needed. If we really want to make a breakthrough, I think we need to think of some other things, and I don't know what it is, but we have tried the chemical and physical, that didn't work, so maybe we need other chemicals or other things to do. But I think maybe we need to really think of something else. Or we just have to conclude that pigs were never really meant to be ruminants anyway, so that's the reason we can't make them do this. So with that, I want to acknowledge members of my lab. These are the students and postdocs that are working for us, and it's not a completely up-to-date photo, but we actually a few more people now. If you want to learn more about our research, you can go to our website here. And as Dr. Easter pointed out before, all information today is on the website, and if you Google us, you will find us here. We have all our research reports. We have a free newsletter every month and so forth, and you can just go to the website and download from there. So with that, Denny, I want to conclude.